Hello, everyone.
David.
Hi. Let's just
Hi,
give
Yvette.
it 1 minute. Hi. It's just 10 PST, 1 EST. Let's just give it a quick minute to make sure that everyone joins. All right, how about we get started? Welcome, everyone. Good morning, good afternoon. This is another webinar hosted by the CHA, the Canadian Hydrogen Association, together with our members and colleagues from the Canadian Nuclear Laboratories, Atkins Realis, and ISO Water. My name is Yvette Vera Perez. I'm the president and CEO at the Canadian Hydrogen Association. And next slide, Pranav. For those of you who are not familiar with CHA, next slide. We are a industry association, not for profit. We strive to be a unified voice for the hydrogen sector in Canada, over 200 members and counting. And we also have a number of affiliates that we have already incorporated so far in BC, Alberta, and Ontario. This is because a lot of the energy decisions in Canada are made also provincially, locally. So we want to make sure that our members have national and international representation, but also boots on the ground regionally. Some housekeeping items before we get started today. I am going to be recording we're going to be recording the event, the webinar, and we would ask that you please stay muted when you're not speaking. The webinar will be conducted in accordance to the CHA's competition law compliance policy. So what that means is please refrain from discussing anything that might be proprietary or confidential to your company. Feel free to add questions in the chat portion of the webinar or in the Q&A section. We will be collecting them all, and we will be asking them towards the very end. Today, we're going to structure our webinar in such a way. First, we're going to have a presenter from CNL, Canadian Nuclear Laboratories. Next slide. We're going to have Justin Morse, who's the Acting Deputy Vice President of Business Development and Commercial Ventures at CNL. Justin is going to be joined by his colleague, Nicholas Kuwahara. Nicholas is Director of Commercialization at CNL. And then this first section of the webinar is going to be a presentation by CNL. Then we're going to move into a second section. It's going to be more like a roundtable, relatively informal. And we're going to have our colleagues from Atkins Realis joining. Today, we're going to have Sabrina Ula. Sabrina is the Director of Program Interface and Nuclear Engineering and Services at Atkins Realis. And last but not least, in the roundtable session, we're going to have someone who's very dear to the industry that we all know and respect and admire, Andrew Stewart. He is the chairman of ISO Water and also co-founder of Hydrogen Optimized. So with this in mind, we're going to get started with our first portion, which is going to be a presentation by CNL. And I think, Justin, you're going to be taking it away. And Pranav, if you want to share that portion of the slides.
Thanks a lot, Yvette. Give Pranav a few moments to just pull these up.
Just give it a time.
1 second.
Yeah, no worries. Take your time. It's a heavy file, and Justin, if you want to start doing a bit of an intro.
I'll just jump in. So, thanks a lot, everyone. I'm glad to see everyone here virtually this morning for those on the West Coast. We'll walk through a few pieces. You can go on to the agenda slide, Pranav, please. So we've kind of structured this around these series of questions. First off, well, why heavy water? Not everyone might be aware of the current uses or historical uses of heavy water. So we're going to do a little bit of a history lesson, and a little bit about who we are as CNL. The important piece here, what's the market, and how does our synergistic production actually work? And then what's next? As a bit of a primer, starting kind of from the bottom, the key for us is we are looking for partnerships with hydrogen producers. We've pulled together these few slides just to introduce folks, but ultimately we're looking at follow-up conversations about deployment. You can jump on to the next slide, Pranav. So why heavy water? On into the next, please. Well, heavy water is a bit of Canadian history. So prior to shutting down production in 1998, Canada was actually a world leader in all things heavy water. AECL and now CNL remain the world leaders in D2O, deuterium oxide, heavy water related technologies. Beyond this technical expertise, which we developed over about 50 plus years, there is also a secondary role that CNL has played, and that is in the management and sale of the Government of Canada's deuterium oxide inventory. Is the presentation not visible to folks?
Is anyone else having this issue? I can see it on my side. Justin, are you able to see as you present?
I can, but I just thought I'd jump up in the chat. So perhaps the focus to grab the presentation makes the most sense. Importantly, we did have commercial scale heavy water production from about 1963 to 1998 when it was shut down. These were historically produced from natural water, which has about 150 parts per million of deuterium, using two key methods, although one of them was deployed in Canada, and that's the Girdler sulfide and ammonia hydrogen methods. So what I've actually got pictured here are two of those, and if you can click once, Pranav. These are two sites from Nova Scotia, one of which is, oh, no, go ahead, go up, there we go. One is the Glace Bay heavy water plant, the other is the Port Hawkesbury heavy water plant. Some of you folks might actually be very familiar with Port Hawkesbury because there's two large-scale heavy water hydrogen production deployments on effectively the same site. So this kind of ties in to the whole story of hydrogen in Canada as well. Importantly, these methods are incredibly energy intensive. They are very toxic environmentally, using either hydrogen sulfide or ammonia actively in the processes, and they're not likely to be the way forward for heavy water production in the Western world going forward. There is heavy water upgrading at Canada nuclear power plants using water distillation, but again, this is adjusting minute amounts, the concentration of the water, but it is still very energy intensive. So this is where we started and where Canada started itself in heavy water. Quick jump into the next one, Pranav. I'm a geneticist, so I'm only going to stick with a very little amount of chemistry here. We've got plenty of chemists on CNL staff that know this infinitely better than I do, but hydrogen really has three isotopes. There's protium, which is normal hydrogen, which has one proton, no neutrons. Deuterium, one proton, one neutron, twice as heavy. Makes some interesting changes to its physical characteristics, and about 150 parts per million naturally abundant. And then there's tritium, which we also deal with quite a lot. In this one, it's one proton and two neutrons, and this is radioactive. So light water, H2O, heavy water, D2O. The important part here is that it has some very important nuclear, physical, and chemical properties based on that extra neutron. A nuclear reactor grade heavy water is virtually pure D2O. Jump ahead. So what is it actually used for? So in nuclear, this is actually a neutron moderator and heat transport fluid for CANDU and other heavy water-based reactors. Happens to be an incredibly good neutron moderator because of that that extra neutron. In terms of non-nuclear, because it behaves similar to hydrogen but not quite, it actually has many uses in electronics, life sciences, environment. One interesting one, if you have a fiber optic internet connection, you probably have a little bit of CNL, AECL, deuterium running into your house, because virtually all of the fiber on the market at this stage actually it contains a very little bit of deuterium. And CNL, through our distributors, IsoWater and others, have been the supplier to the vast majority of heavy water over the last 10 to 15 years. You can jump ahead. So now I'll get into who we are. One important piece is that we have developed as a national lab the several important technologies here and the expertise to deploy them. Let's jump into the next one, Pranav. We were formerly part of Atomic Energy of Canada Limited. We are a science and tech organization with three key missions. One is clean energy for today and tomorrow, restore and protect the environment. We actually are responsible for cleaning up historical radioactive waste on our site and others. And we contributed to health of Canadians. We are actually an odd beast in Canada because we work under a government-owned contractor-operated model. Our headquarters are at Chalk River, but we work with the government. We are not part of the government formally. Jump ahead. So what's our role in this conversation? So AECL was historically responsible for the development and commercialization of CANDU. That was actually moved over as part of the GOCO transition to our good friends over at Atkins. So the reactors themselves are actually through CANDU Energy Incorporated, an Atkins company, but they require a large amount of heavy water. And historically, that's why AECL ran these plants. Once the need from CANDU disappeared, then the plants were no longer needed because there was a gap between what we knew we needed and then how we would actually move that into other industries. We are the world leader in heavy water related technologies, and we're responsible for managing the Government of Canada's heavy water inventory, as I mentioned earlier. So frankly, we know how to make it, we know how it's made by others, and we know how to sell it. With the support of our distributors. You can jump ahead. So noting that, so what about the market? Next one, Pranav. So pricing, this is going to be an interesting one for everybody in 2023, and we're only going to give publicly available information on here because this is a public forum. But in 2023, India exported about 100 tons, megagrams of heavy water with an average trade value of 460 US, about $600 Canadian per kilogram. We do sell at more than this trade value. That's the one bit of IP you're going to get out of me today, because IP is my world. In terms of non-nuclear market size, North America, Europe, well over 100 tons per year, and the cost based on our modeling for our I've only got one of them mentioned here, is projected to be considerably less than trade value. So CC, and I'll be turning it over to Nick in a few slides to talk about our technologies. But we can make it much less than we can sell it. We do need partnerships with hydrogen producers in order to do so. This is a synergistic process. And again, I'll leave it to Nick to talk through some of the technical. Next slide, Pranav. So who else is out there? I've already mentioned India. They make about 500 tons a year. But with the number of heavy water reactors that are actually going to be coming on stream in India, frankly, a large amount of that is devoted to Indian nuclear reactors. Obviously, currently it's geopolitically challenging to work with India, and they are using environmentally damaging methods. So we are exploring green deuterium. Iran publicly does actually make a little bit a year. China and Russia are rumored to, but really the important part is over here on North America, Europe, and South America. There is no production in the Western world of large amounts of deuterium. There was a plant in Romania that was shut down in 2015, and a second plant in Argentina, which that's been in maintenance mode since 2017. So there is a huge opportunity here for a stable and predictable supply of deuterium oxide heavy water to the market at this point. Jump ahead, please. And some interesting policy to consider as well. Recognizing that everyone here is working within largely within the green sector in hydrogen production and so on. One interesting piece for deuterium is that there is actually a tax credit as part of decarbonizing our efforts to decarbonize Canada that make any equipment that is dedicated to the production, cleaning, recycling of deuterium, about 30% tax credit, which obviously for a large capital expenditure is not small. Working at something like a hydrogen plant, where I believe largely the market for that hydrogen is offshore. This is a tangible and solid connection to decarbonizing Canada at the same time. And again, I'll leave it to Nick to talk about the specifics, but the process we have is synergistic. It is not additional energy. It is additional product, in this case deuterium as well as hydrogen, from the same stream. We're effectively mining that the deuterium out. The hydrogen doesn't really get affected. It goes right back into the stream. You have two products effectively for the same production line. Next slide, Pranav. So on that, I will turn it over to Nick to take us through some of the specifics at a high level.
Thanks, Justin. So yeah, how does the synergistic heavy water production work? Back in the day, CNL, which used to be part of, we used to be part of Atomic Energy of Canada Limited, and we developed a proprietary platinum-based isotope exchange catalyst for use in hydrogen water systems. So this catalyst can be used to produce heavy water using different processes. When we use it with water electrolysis, we call it combined electrolysis and catalytic exchange, or CECE. When we use it with the steam methane reforming plant, we call it combined industrial reforming and catalytic exchange, or CIRCE. And it can also be used in a standalone format called the biothermal hydrogen water, or BHW. Next slide, please. So CEC, go back one. There. So the CEC is a synergistic process, as Justin was mentioning, that extracts deuterium from a hydrogen stream produced by an electrolysis cell. And it uses our proprietary platinum-based catalyst. It has negligible incremental energy requirements, so there's no extra electrolysis required in this case. It's got no impact to the hydrogen production capacity, and it doesn't use any toxic substances, unlike the Girdler sulfide process, which uses hydrogen sulfide, or the ammonia hydrogen process, which uses ammonia. So CNL's CECE process can make about 10 megagrams per year, so 10,000 tons of heavy water per year, if you've got 100 megawatts of continuous electrolysis, or about 1,000 megagrams of hydrogen can get us about 1 megagram of heavy water. So if you click once, Pranav, please. So here's a rough block flow diagram of the CECE process. The blue dotted line arrows are the hydrogen gas, and then the black line is the liquid water stream. So if you start on the left, we've got the natural water feed that starts into the large catalyst columns. And in this system, the water flows down and the hydrogen gas flows up, so they're going counter current. and they exchange deuterium and hydrogen between the gas, the vapor, and the liquid. So the lighter hydrogen goes up with the hydrogen gas, and the heavier deuterium goes down in the water. The water goes in at about 150 parts per million. They're on the left into the large catalyst columns. Part of that goes into a large E cell, gets electrolyzed and produces hydrogen. The rest of the heavy water bypasses the E cell and goes on to another medium catalyst, a series of medium catalyst columns. And that goes through, part of it goes to the medium electrolysis cell. The rest of it goes to a small catalyst column. And again, the small catalyst column, the water goes out. Some of it goes to the E cell, small E cell, and the rest of it is our product heavy water. For the hydrogen stream, it gets electrolyzed in the various E cells and goes up through the catalyst columns, exchanging deuterium and hydrogen all the way through. Next slide, please. So Synergistic also is a synergistic process that extracts deuterium from a hydrogen stream produced by steam methane reforming. Again, it uses our proprietary platinum-based isotope exchange catalyst, negligible incremental energy requirements, no toxic substances, doesn't impact your hydrogen production capacity. So the Synergistic process is basically the first enrichment step towards making heavy water. The output from Synergistic brings your water from about 150 parts per million to 6,000 parts per million. So you increase the concentration by a factor of about 40. And then you combine the output from Synergistic with other processes to enrich from your 6,000 parts per million up to your 99.8 weight percent. So you could have a Synergistic followed by CE steps to get you to your desired concentration. And for Synergistic, about 1,500 megagrams of hydrogen in the steam methane reformer gets you about 1 megagram worth of heavy water at the end. So if you click, turn up, please. On the left, we've got a simple diagram for a steam methane reformer, and on the right, it's a steam methane reformer with Synergistic. So on the left, we've got methane coming in with a hydrogen. It's got about 100 parts per million deuterium, water coming in 150 parts per million. Hydrogen goes out, and the CO2 goes out. When we go for the Synergistic process, your hydrogen is introduced to the system at the top of the catalyst bed, and it flows down through the catalyst bed. The product or the liquid outlet from the catalyst bed gets split off. Some of it is your product to go on to further enrichment. The rest of it goes down to the steam methane reformer, where it's combined with methane to produce CO2, and then the hydrogen that's produced goes up through the catalyst bed to produce just your product hydrogen. Next slide, please. So in the late 90s and early 2000s, the CNL ACL at the time worked with Air Liquide Canada and other partners to design, build, commission, and operate the prototype Synergistic plant in Hamilton, Ontario. The PCP, the prototype Synergistic plant, had demonstrated all three of CNL's technologies that I mentioned. So the first step, on the left there, that's the LPCE1 is the Synergistic. The middle LPCE2, that's the bithermal hydrogen water. And then the third step is the CECE. So we successfully demonstrated all three technologies. You can see those pictures are those large cylinders with the black plates. Those are structured catalyst. And then the other one below it with the beads there, that's our random catalyst. So two different form factors for the isotope exchange catalyst. So the PCP, the prototype Synergistic plant, successfully demonstrated the technologies and produced about 1 megagram per year between 2000 and 2002. I'll pass back over to Justin now. Next slide, please.
So thanks a lot, Nick. And we can get into more details. And obviously, some of that next step conversation will include some technical, because there's tweaks that are necessary to plug this thing in. But it is relatively straightforward. And we do have the expertise and experience to do so. So summarizing what's next and kind of taking things back, we are looking for partners that are producers of hydrogen in order to effectively find our mines. We're looking for hydrogen to mine for deuterium. And we've got a couple of ideas on how that could look, and we can chat about those. We'll chat about some of those in the roundtable, but others would probably stay for one-on-ones. We'll be looking for the partners and working on that feasibility of deployment of the technology, and we are experienced in working on these and negotiating those type of arrangements. Next slide, Pranav. So I'm going to come back to I like my maps, and this really is ultimately a Team Canada approach. This is actually a map that's courtesy of our good friends here at CHA that I believe they built for NRCan. Each one of these large green dots, you guys don't need to be told, are electrolytic-based hydrogen production. Blue dots, steam methane reforming. Like, these are our potential mines for deuterium, and seeing so many dots on this really gives us a lot of hope for this process. One click, please, please, Pranav. So if you remember, I had my little star up front. This is the Port Hawkesbury site. We have used this as a production site for heavy water in that case, because there is a small natural enrichment in the water in that area, in that section of Cape Breton. This is an option for us to go back and kind of remake things a little bit. We are aware that there are some major initiatives in Atlantic Canada and across the country, indeed, to deploy hydrogen production, and we're looking to see who we can partner with to deliver on the promise of heavy water. Effectively, as I mentioned, we're looking to rent these hydrogen streams to mine out the deuterium. There would be obviously some economic benefit to the hydrogen producers in terms of kilograms of hydrogen, kilograms of deuterium produced. But we're currently working on different models, and we'd like to hear from yourselves some of those thoughts. And again, feel free to connect with us individually if these are not things to share directly. But ultimately, what we're looking at is trying to leverage CNL's experience, expertise, and the current and expanding opportunity in deuterium. We'll get into the size of the potential opportunity very shortly, so I don't want to spoil that piece. But we are on the cusp of deploying this production technology, and we're looking to see how best to partner with CHA and its members. On that note, our contact information is here, and I'll turn it back over to Yvette to take us into the panel discussion.
Thank you so much, Justin and Nicholas. My takeaway from this really good presentation is there are opportunities for additional revenue streams when you produce hydrogen, and that's really good news. I'd like now to invite our other colleagues to turn on their camera. Thank you, Sabrina.
Thank you, Sabrina.
And I can hear myself twice. That's a bit much. So someone may want to be muted. All right, so I can only hear myself once. That's better. So I wanted to now have a little bit of a conversation, all of us, about heavy water and the many opportunities. I'm going to start with a very broad, open question to all of you. What brings your company into the heavy water world? I know I heard a little bit from CNL, but in general, what brings you to the heavy water world? Sabrina and Andrew. And Justin, you can also chime in, of course.
Yeah, sure. So
I'll let Sabrina go and take this one.
Okay, great. Hi, everyone. So what brings Atkins Realis, what brings us to the heavy water world? Well, it's CANDU nuclear reactors that brings us to this discussion. As you know, the world is embarking on a nuclear renaissance, and we are talking about nuclear new builds, which is great news. And that includes Canada's own CANDU reactors. looking at bringing those back onto the market for new builds. So CANDU, which stands for Canada Deuterium Uranium, uses heavy water, right? It's in the name, deuterium for deuterium oxide, and it uses a lot of it. And this is the design property. The use of heavy water is actually the design property that enables CANDU reactors to use natural uranium rather than enriched uranium. And that includes the design property for the next generation CANDU reactor, which is the 1,000 megawatt CANDU Monarch. And I'll just explain very quickly what this property is and how the reactor uses heavy water. So it uses it for a moderator and it uses it as a coolant. So a nuclear reactor, the way it works is it generates heat from nuclear fission, right? It's the splitting of atoms. So that heat converts water into steam, which then, pushes the turbines. And in a CANDU reactor, the natural uranium is loaded into the core. And when there's enough of it, the neutrons start a chain reaction of fission. Slower neutrons are better at splitting atoms. So heavy water, because of its property with that extra neutron, it acts as a very effective moderator to slow down those neutrons without absorbing the neutrons. So that's why it is a requirement for the core of a CANDU reactor. Heavy water is also used as a coolant, as I mentioned. It circulates through the core of the reactor, and as the coolant picks up heat, it becomes very, very hot, and it boils the water. It boils water into a high-pressured steam, which is then used to turn the turbine. And the rest, we know what the process of producing electricity and power generation from that is. So as we can see from this visual over here, towards the bottom, we can see this image is a courtesy of the Canadian Nuclear Association. We can see on the bottom in the purple circle, that's the reactor core. You see the rods going through, that's the uranium being put into the rods. The dark blue is the heavy water used as the coolant, and the more turquoise blue is the heavy water used as the moderator, which is used to slow down the nuclear, the fission. The neutrons moving around. So if we're going to talk about now how much water is required for each reactor. For each new Monarch, it's a lot. It's 1,000 tons of virgin heavy water for the first fill. And this is for the 1,000 megawatt Monarch. For existing reactors, we're looking at about 4 tons of heavy water per year needed for makeup water. So that's a bit of a background of how heavy water is used in CANDU reactors and how much is required for each new reactor and existing reactor. At this point, I'd probably like to emphasize the importance of generating heavy water from hydrogen operations. We consider nuclear energy as green energy. It's got a low carbon footprint, and power production from a nuclear reactor is essentially emission-free. So it's important to the CANDU program to also have a low emission method of generating heavy water, which is what we saw from the CNL presentation today on the Synergistic technology for production of heavy water through hydrogen operations. Drew? Oh, no, that's we don't need to show that now.
Thanks so much.
Maybe Andrew can comment.
Yeah, Andrew, perhaps you're, what brings you to the heavy water world?
Well, I've been in the heavy water world for 40 plus years and hydrogen, and I founded KeyDH Technologies, Key Deuterium and Hydrogen Technologies, with a view of developing heavy water production. And that's really been my life of hydrogen and heavy water. It's a great honor to be part of this panel. We've been working with Canadian Nuclear Labs for about 15 years. My very first visit to Canadian Nuclear Labs was about 40 years ago, just to help date myself, and lots of collaboration over the years. Within the key, I think if you could put my slides up, who's got those? Within Key's group, can the slides pop up? I think it's just
two
a couple.
Two ahead, Pranav.
Oh, Okay.
Pranav, give him a second. Can you add Andrew's slides to the chat? I mean to the screen.
I'm sorry. What's that?
Andrew, if you want to carry
Okay,
on, and
I'll carry
hopefully the
on.
slide's gonna be up. Yeah.
So we've invested about $50 million in developing technologies, production facilities, and the market. And it was called the non-nuclear market area. And that's really in the sort of semiconductors, optical fibers, OLEDs. Justin talked a bit about that. And we've got about 300 accounts all around the world. We sell into 25 countries. And it's a very diverse market compared with the nuclear use, where you just only have a couple of customers. We've got hundreds, and they all are kind of in different industries. So it's much smaller scale, but it's much more diverse. And so our basic process, we call it the D2X process, is we work with electrolyzer manufacturers, including our own company, Hydrogen Optimized, which we've developed the electrolyzer at Hydrogen Optimized to be really large scale. We started to do that all before the green hydrogen activities came out. And we do an enrichment in the at these big scale green hydrogen plants. We take some enriched water from that. We move it to ISO water and do a final enrichment there to the specific requirements of our customer. Then we would sell heavy water to this non-nuclear industry. And as we have an internal customer called Dutramed, who actually is a manufacturer of high value deuterium containing products. So that's what we do. And any other slide there? Is that come up there? Event?
Just let me try to find them
one
somehow.
second. Yep.
Yeah. Did you get them, Pranav?
Yes, just 1 second, please.
And so we have a range of facilities. We have a 40-ton per year heavy water production facility for enriching lower percent heavy water. And if we get the slides up, we'll show where we're building out initially a 5 to 20 ton per year heavy water production and moving that towards 200 tons a year in a long-term objective. And so I'd like to show those pictures if I can, if we have the time. But anyway, well, why don't we
Pranav,
carry
are
on?
you able? Yeah,
If we-
no, sorry, Andrew. Pranav, are you able to get them, or should I try to put them in?
I can pull them up if you guys would
Nick,
like.
if you can present, please pull those up.
Yeah.
Pranav, if you could stop presenting, that'd be great.
Okay.
Oh, actually, they're up now.
Oh, there we
Okay.
go. All
There you
right.
go.
So what you can see, yeah, so we're part, as I say, Ice Water's part of this group I founded 15 years ago. And on the right, you see our 40-ton per year heavy water refinery, which does final enrichment of heavy water that we make in the field or recycle from clients or other sources. Go to the next slide.
One more.
And this is our
We're
D2X
having technical
process.
difficulties today.
Yeah, we take the deuterium from natural water, we enrich it partially up, and then ISO water takes that to make.
Oh,
You muted
Andrew, you're
yourself,
muted
Andrew.
now.
You muted
Today's
yourself,
technical
Andrew.
day, everyone.
Okay,
Good.
sometimes people like to meet me. We take the high purity and we go out to the world with it, but also to our own client where we make high value products, for example, semiconductor gas, where we sell that to the companies like LG and SK and Samsung and others. Okay, thank you. Next slide.
One more. Okay.
So here's how we make heavy water from natural water. We start with remote electrolysis plants in the green hydrogen world, hundreds of megawatts. They can be in many different, they can be 50 megawatts here, 200 megawatts there. It doesn't really matter. We do enrichment, and then we transport the enriched deuterium to our own internal facilities in Owen Sound, Ontario, where we've got quite a lot of electrolyzers there, and we can do the final enrichment to the client's needs. Ultimately, in this 10 years plus, we'd like to be able to make 200 tons per year, and in the near term, 5 to 20 tons per year, and just scale up incrementally as we build out or partner with hydrogen plants. And next slide. And so we seek partners, all sites from finance to project partners, electrolyzer developers, technology. And there's my email if you'd like to reach out. Anyway, that's Andrew-Stewart@icewater.com. Thank you.
Thank you. Thanks so much, Andrew. If that's all right, everyone, I'll ask the next roundtable question. And I think, Justin, you made a little bit of reference to this, but I think it's really important because after all, our part of the essence of our work is to try to find opportunities for our members, right? So what is the market for heavy water, for deuterium, and the business case for heavy water? So if all three of you would like to chime in, that would be fantastic.
Well, I'll preface this one with a bit of a heads up to Pranav. Pranav, if you can actually prep the Atkins Realis slides. So these are the first two you just had on there. Leave it at this one for now. I'm sure Sabrina would like
Thanks.
that one. So this is a very interesting market. And Andrew's likely going to grin at this one because, frankly, if we can get it, we can have it sold yesterday. And this is not typical. The challenge really is supply and predictable and reliable supply, because it hasn't been produced in the Western world in quite some time. And there are huge geopolitical challenges to accessing what little supply there for new production there actually is. The prices are very solid, and both with the possibility and the growing possibility of new CANDU and extra needs within the nuclear and non-nuclear market, the possibilities here are really immense. And the offtake agreement, the transfer from I have an idea to I've got a buyer, that issue isn't an issue here. Like most buyers, most of the distributors and downstream users would be more than happy to sign on and say, I will take what you can make. If anything, it'd be a bit of fending off some of the market, as we found it in the recent years as supply has gotten tighter and tighter. So I'll hand it over to Sabrina on that note, because there's quite a bit on that end.
Yeah, thank you, Justin. So bringing it back to CANDU reactors and nuclear, if you were watching what was happening with COP28 and COP29, it showed a lot of support, large support for nuclear power ramp up. And the declaration was something like tripling nuclear power by 2050. And what came out of those conferences was over 30 countries that have projects now on the horizon, new nuclear projects on the horizon. If CANDU, projecting that CANDU reactors, it's okay, we don't need this slide just yet, capture just 5% of that, just 5% of the projection until 2050, we're talking about over 50 new CANDU reactors built by 2050. And each one of those reactors requires 1,000 tons of heavy water at 99.8% purity of heavy water. So we're looking at a market just for 5% capture rate of 50,000 tons of heavy water. That's a lot. So maybe I'll just let that one sit in terms of the market that we're looking at right now for CANDU reactors.
Thank you so much. Okay, Andrew, yeah.
So to put it in the terms of the audience, and we think of gigawatts of electrolysis required, my back of the envelope calculation for the nuclear market, just the CANDUs from the from Atkins, it's about 20,000 gigawatt, 20,000.
50,000. About one gigawatt is about 100.
Yeah, it depends if you're making it in 20 years or the production rate,
course.
but it's a heck of a lot. What our needs, 200 tons a year, not over time, that's about 2 gigawatts in scale. So the nuclear use is very big, and our demand at 2 gigawatts is not exactly small in the context. That's if everything was made in the context of water electrolysis. And of course, there could be a variety of different production methods, including the Cersei.
Yeah, and certainly. So the key here is we want to get this conversation going. We've been internally figuring out how to start addressing this problem, and this is a bit of the first step in that. And we're very thankful to Yvette and the CHA. Back to you, Yvette.
Yeah, 20 gigawatts was the number I was looking for.
Yeah. Thanks so much. And I think in layman terms, the market is huge, and that's that's good to know. I know that we're a minute or two behind time, but I really had some really good questions for the roundtable, so I'd like to carry on if that's okay. Okay, market is huge. We have established that. What is the timeline to get to that market? And somebody mentioned 20 years, etc. But timeline, what do you guys say?
Maybe I'll go for that one, and maybe now we can put up that next slide.
Yeah.
Which I have. There we go. Now I'm ready to show it. So this is basically projections. These are not contracts. I just want to make that very clear. These are projections for readiness and planning of when each 1,000-ton of heavy water would need to be ready if we're talking about those 50 new CANDU reactors required for Canada and globally. So if we take the projection from 2032 to 2046, we're looking at the first 1,000 tons needing to be ready by 2032, which is in time for commissioning of a first Monarch reactor. So as you can see, it's going to move, right? 1,000 tons every year, and by the time we get to 2036, we're looking at 3 tons as we start to serve the international market for commissioning of new reactors. And 2032 will come fast. For those of us who are still writing 2024 on everything, right? It is 2025 actually, and there's a lot of work to be done before we get to that 2032 stage, which is, as Justin mentioned, setting up these partnerships, doing the concept, doing the design, building these facilities by the time we get around to actually producing that first 1,000 tons by 2032. So this is just a snapshot of what a projection could look like for timeline.
Thanks so much. This is good to know. It puts things into perspective. And before we move into the Q&A, and I'm happy to see that everyone is putting in questions, can we reiterate the opportunities for members in the audience? What do you see the opportunity could be like? I know we've talked a little bit about it, but to me, it's an important takeaway.
Perhaps I'll start with the simple one. This is a certainly solid revenue generating opportunity for hydrogen producers. This has long-term potential, and we're looking to start building bridges and partnerships right away. So this is a good time to be discussing this.
I can comment. So our founding vision was based on my actual past experience, where we're developing an electrolysis project in my previous company that was about 180 megawatts, and then we're adding on to that the deuterium enrichment. And we couldn't sell the deuterium. We didn't understand the market was actually oversold. And but I knew very well if I could sell deuterium, I could make my electrolyzer more competitive. And so essentially having those two products, hydrogen and deuterium, makes the rugged cell, hydrogen optimized rugged cells, very attractive. And it could also make other electrolyzers attractive too. And that's why we're looking to partner with both rugged cells from hydrogen optimized, as well as potentially other electrolyzer vendors. And IsoWater, again, has a great number of counts, and we need feedstock. And so we're developing, that's why we're into this.
Thank you so much, Andrew. We have so with this, I'll conclude the this portion of the roundtable. But before that, Andrew, Sabrina, and Justin, any last words before we move into the Q&A?
Yeah, perhaps for me, and for CANDU reactors, I would say that producing heavy water via a hydrogen plant, it's important, right? Because it not only contributes to nuclear power through CANDU reactors, but it would enable a Canadian solution through and through, right? So Canadian solution with a Canadian hydrogen producer, for heavy water with our power reactors. So maybe I'll just leave it with that thought.
Yeah, and with that, I have to thank you, Sabrina, because you stole my conclusion line. No, but that's a very important point that definitely has to be made. I had some questions
I would just
here.
add a little footnote,
yeah.
though, that from what we do, we look at the global supply of where we can do enrichment. And I think Canada is very important, but there's a whole world out there with electrolysis.
Yeah, absolutely. Absolutely. So I had some questions here, but I see that we have a lively discussion here. Would anyone from the chat like to raise your hand and ask the question yourself? Unmute and ask a question, or would you like me to go ahead? I'm gonna get ahead and get started, but feel free to raise your hand. Some really good, interesting questions here. One question, and that's from Gillian Johnson. Is there a minimum viable project or product capacity size, either based on technology or economics, that you'd like to I guess to present to us? Justin, Sabrina, Andrew, Nicholas.
I could comment. Our focus is multiple small plants and bring them up. Our target is about 50 megawatts as being where we'd like to be. And our product in electrolysis is 50 megawatt modules. We would have a standard 5-ton per year design to extract the deuterium, but we could go smaller. I think 25 megawatts is not unrealistic, but again, we could also do it 500 megawatts. So it's very scalable.
Yeah, and I'll echo that with Andrew. At this stage, there is no production. That's the simple fact. So we are looking at anyone interested. The economics are not going to be identical, but they do scale pretty well. A small plant, say a 2-ton plant, is something that is in the cards as more of a demonstration scale. This is not going to solve. This is a drop in the bucket, literally. And I recognize I'm talking about water. That it's simply not enough, but it is a springboard to those 10, 20, 50,000 ton type of scaling, right? So we're looking right across the board. So distributed model, as Andrew's mentioned, is on in the offing for us, but also centralized large plants or a combination. The need at this stage, we're not going to turn down those possibilities, because I think there's value in any stage and any level of deployment. It might be de-risking it for larger scale deployments. It might not be fully economically viable itself, but it's part of the path to large scale.
Thank you.
I would echo that. I would echo that. Multiple facilities can be deployed for this.
Thank you so much. And I just heard a bit of a heavy water joke from Justin there on dropping in a bucket. That's good. That's good. Keep them coming. So there's quite a few questions. We won't be able to go through all, but there's 2 questions that have the same theme, and I'm gonna read them both and let you chime in. So, is power availability needed to produce heavy water in the future going to be a challenge? How is power going to be provided? And one along those lines, can you speak to the generally to the electricity demand for producing heavy water for electrolysis? Is it around 50 kilowatt hour per kilogram of hydrogen? So I guess in essence, electricity and demand. How do we address that topic?
I'll actually do that one, and I'll actually take another one off the list at the same time. In terms of power availability, this it depends on where the hydrogen is coming from, obviously. If you're looking in Atlantic, a lot of offshore, onshore wind is the likely power source. In other cases, the steam methane reformers are not. They're using separate power sources through methane, I believe. But the important piece here is this is synergistic. This is not 1 gigawatt of additional electricity needed. It is 1 gigawatt, and you get your hydrogen stream. You still get your hydrogen, but you're also pulling off deuterium. You're getting a second product for the same electron. That's an important one. Now, is it going to be a factor? Absolutely, but it's the same factor for the hydrogen plant to begin with, especially electrolytic hydrogen. If you don't have the electrolysis, if you don't have the electricity, you're not going to get the electrolysis, which means none of these things are going to work, right? So they're interdependent, but from my view, because they are synergistic, you're getting, again, 2 products, 1 electron. You're not adding another gigawatt of need to your system. You're adding a second product with very little incremental cost. That's the key to how this is working. And the other question here was whether or not these had to be co-located. So the Girdler sulfide, it had to be co-located on a nuclear site once the Glace Bay and Port Hawkesbury were closed down. I don't believe they were AECL managed sites, but I don't know if they were dedicated nuclear sites. But for these, completely distributed. This process does not demand being hooked up to a Bruce type of plant for steam. Those are the older ammonia, hydrogen, or Girdler sulfide processes. We don't really need to be right next to or built on a CANDU site at all.
And I guess ISO water is an example of that.
Very distributed.
Yeah. And that actually may help with the next question is unfortunately, I think the last question that we're going to be able to answer today, and it's about price. So it looks like a year-on-year basis, the prices of heavy water have increased, and that could be refraining customers, so that would be the users, of to use deuterium chemistry. What do you see prices and more than the number itself, but stability of deuterium prices in the future as the supply increases? I know you don't have a crystal ball, but if anyone would like to tackle that one.
I can give it a bit of a view from the non-nuclear use. There's a huge number of applications. Some are sensitive to the price of deuterium, and they've kind of dropped out as the price has gone up. And then there's others that can tolerate a higher price. We don't know how much higher they can really tolerate it, and without the demand dropping. And I think there's probably some applications and then there's applications that must have it. NMR spectroscopy, for example, that has to have deuterium. And that's one of the drivers for us. Like, we couldn't imagine a world without science, and making deuterium for NMR spectroscopy is required. And there's a handful of others that either have deuterium or they don't exist. So anyway, it's a range of outcomes and value. So
I'll jump on that one, and it really is a tale of two markets. The nuclear large scale heavy water market has different dynamics than the more, well, there is a large scale market for non-nuclear, although it's not quite as large at this stage. The markets will react differently, and we are working with partners to ensure for a large scale deployment like a CANDU, price at startup is got to be determined relatively early. Otherwise, you're going to have a toy that you can't afford the keys to, right? And we obviously don't want that scenario. So stable, solid supply with reliable and consistent pricing for nuclear applications is definitely more important. It's more important for that stability because it has to be there on day one. It has to be delivered. Has to be delivered on a certain budget. Otherwise, it affects it's a trickle down effect for the rest of the economics, right? But in terms of smaller scale applications, they're less sensitive to price changes. But the fact is, if you're changing a core to anyone's process, and you massively adjust the price, then there's going to be a breaking point. Whether or not we're there, it remains to be seen. Again, in a very supply starved environment, price becomes less and less of an issue the more important that the product is, right? But there is going to be a point where this has to stabilize. Don't know if we're there yet.
Yeah, no, and but that's all right. That's a good way to end the webinar. We are at time, everyone. We could not answer all the questions, but Pranav, if you help me gather them, we can send them to the panelists here, and they can answer them in writing. Thanks so much, everyone. My key takeaways in very, very layman terms: market is huge. Canada has everything it takes, nuclear capacity, nuclear know-how, hydrogen know-how, and it's just on us to get to this big revenue stream for all of us producing hydrogen. Thank you very much to CNL, to AtkinsRéalis, and to ISO Water. And thank you to the members that helped us with this lively discussion. Thanks so much, everyone. Have a good day.
Thank you very much, everyone.
Thank you, everyone.
Cheers.
Bye.
Thank you. Bye-bye.